Hello everybody, welcome into another lesson. So today we are going to talk about how to solve systems of linear equations in three variables. So here we have this system of equations where you have 17x minus y plus 2z equals negative 9, x plus y minus 4z equals 8, and then 3x minus 2y minus 12z equals 24. Well, in general, the number of variables you have are the number of equations you need to have. So if we only had two equations, you would often end up with infinitely many solutions because one of the variables would be set to have infinitely many solutions, which would mean the others would too. Now, if I had more equations, let's say I had four equations for only three variables, there would often be no solution. So, usually you need to have, if you have only two variables, you need two equations. If you have three variables, you need three equations to be able to find the point of intersection. But yesterday's lesson, we talked about graphically what these equations represent. They represent triangular planes. Well, we have three of them. We need to figure out at what ordered triple do they intersect at. That's the whole goal. When we were doing it with only two variables, we were figuring out the ordered pair where two lines intersect. Now here in three variables, we're trying to figure out the ordered triple where three planes intersect. So how you're going to do this is much like with the two variables. You're going to use a lot of elimination. Now, it's a little bit different when you get into three variables because what you want to do is you're going to take two of these equations to start with, use elimination to try to eliminate one of the variables, and get down to a system of two equations with two variables, and then solve that system and get the value of one variable, then use back substitution to find the value of all the others. So let me show you. Here, I'm going to start with 17x minus y plus 2z equals negative 9, and x plus y minus 4z equals 8. So if I add these two together, I can eliminate the y variable. So let's go ahead and do that here. 17x minus y plus 2z is equal to negative 9. And then we have x plus y minus 4z is equal to positive 8. Notice if I add these two together, I'll eliminate the y variable. So let's go ahead and do just that. You end up with 18x, the y's go, 18x minus 2z equals negative 1. Right? You have that. Now, what you also can do is you can take any of these other two equations and get a second equation of only two variables. So I'm going to take twice equation 2. So I'll take 2 times equation 2, which would be 2 times the quantity of x plus y minus 4z, set that equal to 8. Plus, I'll take my third equation, 3x minus 2y minus 12z, set that equal to 24. Well, if I do that, distribute the 2, I'll end up getting 2x plus 2y minus 8z, excuse me, I almost distributed there. Minus 8z would equal 16. And then, of course, I'll add the second equation, 3x minus 2y minus 12z equals 24. Now that I've multiplied the second equation by 2 and I'm adding the third equation to it, notice I can eliminate the y variable yet again. So with both of these equations, you want to eliminate the same variable. Let me go ahead and add these up here. If I do that, 2x plus 3x is 5x, 2y minus 2y, the y's go away, minus 8z minus 12z, that's minus 20z, is going to equal 16 plus 24 is 40. All right. Now I have reduced this down to two equations with two variables. So let's go ahead and do that here. I'm going to end up with 18x minus 2z equals negative 1. And then I'm going to end up with 5x minus 20z equals 40. All right. Well, you can either try now to eliminate the x or eliminate the z. I think it's going to be a lot easier to try to eliminate the z. If I take and multiply this top equation by negative 10, I can eliminate the z. So let's go ahead and eliminate the top. Let's multiply the top equation by negative 10. Negative 10 times 18x is going to be negative 180x plus 20z equals positive 10. And then I'll end up, of course, I'll be stuck with 5x minus 20z equals 40. Well, if I add these two new equations together, I can eliminate z. So let's go ahead and do all that. So negative 180 plus 5, that's negative 175x. The z's go away, but 10 plus 40 equals 50. So now I have negative 175x equals 50, which x is going to give me negative 50 over 175. You can divide both by 25. If you do that, you get negative 2 over 7. So x would be at negative 2/7. So we found x to be negative 2/7. Now, since we found our x values, let's go ahead here. We can take our x value, put it into any of the two equations we got with just x and z, and solve for z. So let's deal with 18x minus 2z. So if I take 18 times negative 2/7 minus 2z equals negative 1, well, I'm going to end up then getting, of course, negative 36/7 minus 2z equals negative 1. Well, now I want to get that negative 2z by itself. Negative 2z would equal, so 36/7 minus 7/7 would be 29/7. 2z equals 29/7, which means z would have to equal negative 29/14. So we found the value for z. Now let's go ahead and find the value for y. We know our x value to be negative 2/7. We know our z value to be negative 29/14. Take both your x and z values, put those into any of these three equations, and then solve for y. I'll go with the third equation. It actually... No, let's go with the second. So x had a value of negative 2/7, right? Negative 2/7 plus your y value, which we don't know just yet. Then you have negative 4. You have minus 4 times negative 29/14. All that is going to be equal to 8. So you'll have negative 2/7 plus y. This would become plus 58/7. would equal 8. Well, negative 2 sevenths plus 58 sevenths would give you 56 sevenths. What is 56 sevenths? That's 8. 8 minus 8 is 0, so the coordinate for y would be 0. So now we found all 3 points. We found our x, our y, and our z coordinate. So now you just put them in an ordered triple. Your x coordinate was negative 2 sevenths. Your y coordinate was 0. So you do your x, your y, and then your z was at negative 29 fourteenths. So the ordered triple negative 2 sevenths, 0, and negative 29 fourteenths is where these 3 planes come together and intersect at that ordered triple there. Negative 2 sevenths, 0, negative 29 fourteenths. And I got more equations here. I know it's a bit of a hot mess, but the more variables you have, the messier it gets. And there are even equations, there are 4 variable linear equations, which we're not going to do in this course, because I'd probably run out of room on the board. And plus, you'd probably want to use a graphing calculator for that anyway. It gets kind of awful once you get beyond a 3 equation, a 3 variable. All right, next one. Negative 2x plus y plus z equals negative 2. Then you have 5x plus 3y plus 3z wow, that's awful, equals 71. And then you have 4x minus 2y minus 3z equals 1. Well, of course, now we have this system here where you have negative 2x plus y plus z equals negative 2, 5x plus 3y plus 3z equals 71, 4x minus 2y minus 3z equals 1. Well, we want to, again, try to look for our first variable we can eliminate. I think in this case we want to try to eliminate z because between the second and third equation you have a 3z and a minus 3z. So what you can do, let's try to eliminate z with all of these. I'm going to say, let's actually start with the first and second equation. Let's multiply the first equation by negative 3, so you get a negative 3z. So take negative 3 times that first equation of negative 2x plus y plus z equals negative 2. And then keep your 5x plus 3y plus 3z, set that equal to 71. You end up with 6x minus 3y minus 3z equals 6. Then you still have 5x plus 3y plus 3z equals 71. All right, well, what you're going to end up having here, if you add these, you're definitely going to eliminate the z variable. So 6x plus 5x is 11x. Negative 3y plus 3y, the y actually disappears. We inadvertently did that. Negative 3z plus 3z, well, the z disappears. We just add 6 plus 71 would give you 77. Well, that's going to give you an x value of 7, of course. we already solved for x. And that's okay. You will have that sometimes. Now, why don't we add the second and third equation together to eliminate the z variables? So add your 5x plus your 3y plus your 3z. Set that equal, of course, to 71. Then just straight up add your third equation to the second. 4x minus 2y minus 3z would equal 1. Well, notice your z's are going to go. If you add the second equation to the first, you end up with 9x minus y would equal 72. Well, good news is we already know the value of x. We already know that. If you just take 9 times the x value of 7 minus y, you set that equal to 72. That, of course, would give you 63 minus y equals 72, which would give you negative y equals 9, which would give you a y value of negative 9. So we actually just found y. We now know x and y. Let's go ahead and put these two values into any of these above equations, and we can solve for z. So let's do the top one. We'll take negative 2 times our x value of 7 plus that y value of negative 9 plus z, set that equal to negative 2. Well, negative 2 times 7 is negative 14. Then you have minus 9 plus z equals negative 2, which would give you z minus 23 equals negative 2, which would give you a z value of 21. So we have just found the ordered triple where these three planes intersect. So x is at 7, y is at negative 9, z is at 21. So the ordered triple where these three planes intersect will be 7, negative 9, and 21. And sometimes it is possible to eliminate two variables at once. You will sometimes have that. All right, what's next? X minus 9y plus 4z equals positive 1, rather. Okay. Then we have negative 4x plus 18y minus 8z equals negative 6. Then you end up having 2x plus y minus 4z equals negative 3. So here is another linear system with three variables. So first thing, again, look for what variable you want to play with to eliminate. Well, between the first and third, you can directly eliminate z. So my vote is we go for z. Let's add the first and third equations together to get your first equation. So take x minus 9y plus 4z equals 1, and then take your 2x plus y minus 4z equals negative 3. Just simply add these two equations together. You'll end up with 3x minus 8y, the z's are gone, would equal negative 2. So there's your first equation with only two variables. You got 3x minus 8y equals negative 2. All right, now to get our second equation with only two variables, why don't we multiply the first equation by 2 and add it to the second equation? So if I take 2 times my first equation, and then just simply add my second equation to it, the z should disappear. So first, let's do the multiplication. That's going to give me 2x minus 18y plus 8z equals 2. And then I'll have negative 4x plus 18y minus 8z equals negative 6. I can just add these together and eliminate my z variable. Well, 2x minus 4x, that's going to end up giving me negative 2x. Negative 18y plus 18y, that goes to 0. We actually eliminated the y variable again also. And then 8z minus 8z, we eliminated z on top of that. So negative 2x would equal 2 minus 6, which is negative 4. So we're just left with negative 2x equals negative 4, which would give you x equals positive 2. So we inadvertently eliminated two variables again, which it's nice when it works out that way. Now, we could easily solve for y by putting this x value into the equation of 3x minus 8y equals negative 2. So take 3 times 2 minus your 8y, set that equal to negative 2. That would give you 6 minus 8y equals negative 2, which would give you negative 8y is equal to negative 8, which means y equals 1. So we just found the value for y to be 1. Now, we know both x and y. Go ahead and put these into any of these equations here, any of these three original equations, you can solve for z. So I'm going to do the bottom equation here. So take 2 times your x value of 2 plus your y value of 1 minus 4z, set all that equal to negative 3, which would give you 4 plus 1 minus 4z equals negative 3, which would give you 5 minus 4z equals negative 3, which means negative 4z would equal negative 8, which would give you z is equal to 2. So now we found all three coordinates of the ordered triple. So the ordered triple will be your x coordinate of 2, your y coordinate of 1, and your z coordinate of 2. So the ordered triple where these three planes intersect is at 2, 1, 2. That's exactly where they intersect, at 2, 1, 2. I know these are a bit awful because we have variables like crazy going on, but without using computers or graphing calculators, this is the best we got. All right, what's next? So we have 2x plus y plus 2z equals 7. Then we have 2x minus y plus 2z is equal to 1. Then we have 5x plus y plus 5z equals 13. All right, So here's another system we got to solve, but what variable would be best to eliminate? I think it's obvious we want to go with y by adding equations together, because you have a positive y, a negative y, and a positive y. So the coefficient's always 1 on all three of those, just one of them's negative. I think that's obviously your best one. If you can get away with just straight up adding and not having to do a bunch of multiplication with the elimination, that's the best way to proceed. So let's start by adding the first and second equation together. So take your 2x plus y plus 2z, set that equal to 7. Then take your 2x minus y plus 2z, set that equal to 1. And then just simply add these together, and you can definitely eliminate your y variable. 2x plus 2x is 4x. Y minus y is 0. 2z plus 2z is 4z. And then 7 plus 1 is 8. So your first equation should be 4x plus 4z equals 8. Now go ahead and take your second and third equation and do much the same thing. You can add them together. So take your 2x minus y plus 2z, set that equal, of course, to 1, which it is. Take your 5x plus y plus 5z, that'll equal 13. And again, you can eliminate your y variable if you do that. If you just simply add the first and second equation, you'll end up with 2x plus 5x is 7x. And then you'll have negative y plus y, the y goes, 2z plus 5z, that would be plus 7z, would equal 1 plus 13, which is 14. Alright, so we'll go ahead and add 4x plus 4z equals 8, and then we have 7x plus 7z equals 14. Well, there is a way to make this a lot easier. Instead of having to multiply one equation by 4 and one by 7 and one by 4, notice everything in the first equation has a common factor of 4, right? So you can divide everything by 4, which would give you x plus z equals 2. And then the second equation, everything has a common factor of 7. You can divide everything by 7, giving you x plus z equals 2. You have two equations of the same thing. So when you go to subtract the second equation from the first, what are you going to get? You'll end up with 0 equals 0. So remember what that means from the two equations. That means you have infinitely many solutions. There are infinite solutions. And sometimes you'll have that because these planes, two or more of them, could overlap significantly. So there are infinite solutions. But I also want to show you how some books notate the solution. There's another way to write infinite solutions. If you have no solution, there's just no solution. But infinite solutions, what you're going to do, in this case, I would take your z variable. Z would equal a. Z is going to equal a, right? The reason we pick a represents any arbitrary constant whatsoever. So that means no matter what value I stick in for z, it's always going to work. It'll always work. Next thing I would do with that a, solve for your x. So you would take x plus a equals 2, which means x equals 2 minus a. And then take that 2 minus a, and then your a, put those into any of these equations. So take 2 times that 2 minus a, plus y, because we don't know y yet, plus 2a, set that equal to 7. And then you have, of course, you'd have 4 minus 2a plus y plus 2a equals 7. While the a's go, you would end up just having y plus 4 equals 7, which would give you y equals 3. So, yes, you have infinite solutions, but the y value is always going to be 3. So how would you list this in an ordered pair? That's probably what you're wondering. How am I going to list this in an ordered pair? List your x-coordinate first of 2 minus a. Your y-coordinate's always 3, and then your z-coordinate's just a. Those a's represent any arbitrary variable. We set z equal to a, then we solve for x, and then we put those together, solve for y. So you might see the solution in a book listed to 2 minus a, then 3, then a for the order triple. That if you ever see an a, that means there's infinitely many solutions. But the y variable is always 3. It's always 3. So that's something to know about infinite solutions, especially as you get into 3 or more variables. We could have done it with 2 variables actually also, but I mean, we didn't see a need to. But when you get into 3 variables, you could have one of the coordinates that's a regular number, and then the others are just arbitrary constants. That's why we do that. Okay. So we have 7x minus 3y plus 4z equals negative 14. Then we have 8x plus 2y minus 24z is equal to 18. And then for the third equation, we have 6x minus 10y plus 8z equals negative 24. This is going to be a fun one. We have some big numbers. So here we go. Here's our system. We have, again, 7x minus 3y plus 4z equals negative 14. 8x plus 2y minus 24z equals 18. And then 6x minus 10y plus 8z equals negative 24. So we need to pick a variable to eliminate. I don't think we want to go with x because we'll be multiplying by 6 and 7 and 8. Y, we'd have to multiply some of them by 10. I don't think we want to go with y, but z, 4, 24, and 8 are like perfect multiples of each other. They're all perfect multiples of 4. We can multiply the first equation by 6, which would give you a 24z, and would eliminate the z variable. So let's take 6 times the first equation of 7x minus 3y plus 4z equals negative 14. And then we'll just keep our 8x plus 2y minus 24z equal to positive 18. First, do your distributive property. So 6 times 7x, well, that's 42x. And 6 times negative 3y, that's minus 18y. 6 times 4z, that's positive 24z, would equal now negative 14 times 6. That'd be negative 84. And then you're going to have, of course, your 8x plus 2y minus 24z equals 18. Now just simply add your two equations together. You can eliminate the z variable. So 42x plus 8x, that's 50x. Negative 18y plus 2y, that's negative 16y. 24z minus 24z, that's gone. Negative 84 plus 18, that'd be negative 66. So you have 50x minus 16y equals negative 66. Now, if I want to get a second equation, if I take 3 times the third equation, I'll end up with another positive 24z. And then I'll have this negative 24z. That would eliminate the z variable a second time. So let's take our 8x plus 2y minus 24z equal to 18. And then we're going to take 3 times that second equation of 6x minus 10y plus 8z equals negative 24. Well, that's going to give us, if we multiply the second equation by 3, well, you still have the first equation, 8x plus 2y minus 24z equals 18. 3 times 6x, that's 18x. 3 times negative 10y, that'd be negative 30y. 3 times 8z, well, that's plus 24z. That would equal 3 times negative 24. That's negative 72. Now you can add these two equations together and get rid of your z variable. So 8x plus 18x, well, that's going to end up being 26x. 2y minus 30y, that'd be minus 28y. Negative 24z plus 24z, the z's gone. But 18 minus 72, what's that? That'd be negative 54. So you are left with two equations of 50x minus 16y equals negative 66. And then you're left with 26x minus 28y equals negative 54. Well, none of this is particularly pleasant. None of this is going to be pleasant. So we need to pick a variable to eliminate again. You can either try to eliminate x, multiply the first equation by 26 and the second equation by 50 and subtract, or you can multiply the first equation by a negative 28 and the second by a 16 and add them together and eliminate y. I think we're going to do the y approach. So again, I know this is awful, but I'm going to recommend we try to eliminate the y. So multiply your first equation by negative 28. Then multiply your second equation by positive 16. Yeah, this is going to be awful. I'm not going to lie to y'all. This is going to be pretty bad. We're going to have some really big numbers. So now let's go ahead and distribute that negative 28 through everything. I mean, this is going to not be pretty. Yep, that gives you negative 1400x. Then take negative 28 times negative 16. That'd give you positive 448. Now take negative 28 times negative 66. Yikes. That would give you positive 1,848. All right, that's your first equation. Now let's take the second equation, multiply it by 16. So 16 times 26, that's going to give you positive 416x. Now take 16 times negative 28. That'll give you minus 448y. Now what is 16 times negative 54? That'd be minus 864. So now all we got to do is add these two equations together. We can get rid of the y variable. So what you're going to end up with is something not very nice. That would give you negative 984x. The y's go, that's going to be equal to, now we need to figure out 1848 minus 864. Well, what do you know? That gives you positive 984, which means that x would equal negative 1. All that work to get that x equals negative 1. Not pretty, is it? But we now know the value of x. We can plug it into one of these two equations we got and solve for y. I'm almost actually feeling better if I put it into the 50x minus 16y. Why don't we do that? So take 50 times that x value of negative 1 minus 16y, set that equal to negative 66. Well, that's going to give you negative 50 minus 16y. Take the negative 50 to the other side. You would actually end up getting negative 16y equals negative 16, which would give you y equals positive 1. So now we have x equals negative 1 and y equals positive 1. Pick any of your equations to stick it into and solve for z. I'm going to take the first equation. So if I take 7 times my x value of negative 1 minus 3 times my y value of 1 plus 4z, I'll set that all equal to negative 14, which would give me negative 7 minus 3 plus 4z equals negative 14. Yeah, I know, I'm running out of room, right? Well, I'd have negative 10 plus 4z equals negative 14. Add 10 to both sides, you just get that 4z equals negative 4, which would give you a z coordinate of negative 1. So now we know our x, y, and z coordinates of the ordered triple. You'll end up getting the ordered triple negative 1, 1, negative 1. That's where these three planes would come together, is at negative 1, 1, and negative 1. Yikes. All that work just to solve for one order triple. And I'm going to do just one more, then we'll be done. Sometimes I think I need a bigger board, but they're not easy to find and not cheap. Plus, I would run out of room to store them. It's hard enough storing this one in my small place, let alone trying to find a bigger one. Alright, let's do this. Last one. Alright, so we have 3x plus 3y plus z is going to be equal to 30. Then we have 10x minus 3y minus 7z is equal to 17. Then we can come up with negative 6x plus 7y plus 3z is equal to negative 49. So we need to find a variable to eliminate again out of this system, where you're given 3x plus 3y plus z equals 30, 10x minus 3y minus 7z equals 17, and negative 6x plus 7y plus 3z equals negative 49. So I'm personally, at first you would probably think you're going to go with the y, but you're going to be multiplying at least one of these to get rid of the y variable. You'd be multiplying one equation by 7, the other by 3. Whereas if I go for the z variable, we definitely don't want to go for the x variable. That much is foregone there. But if we go for the z, I would just multiply 7 times the first equation to get rid of the z variable for the first equation, and then to do it a second time I can multiply the first equation by negative 3 and add it to the third equation. So I think we're actually going to go for eliminating z. Let's take 7 times our first equation and then we'll just simply keep the second equation the way it is. Alright, so if you multiply that entire first equation by 7, you end up with 21x plus 21y plus 7z is equal to 210. Keep your 10x minus 3y minus 7z equals negative 17 the way it is. Now you can just simply add these two equations and get rid of your z variable. So 21x plus 10x, that would give me 31x. 21y minus 3y, that'd be plus 18y. 7z minus 7z, the z's are gone. Now 210 minus 17, that's going to give me 193. So I'm down to 31x plus 18y equals 193. That's one equation with z eliminated. Now, to figure out a second equation, I could take negative 3 times the first equation and add it to the third equation to get rid of z. So let's do that. Negative 3 times our first equation and then let's just keep our our third equation the way it is. So let's go ahead and distribute this negative 3 into the first one. I would end up getting negative 9x minus 9y minus 3z equals negative 90. And then add this equation, the third one, which would be negative 6x plus 7y plus 3z would equal negative 49. So negative 9 minus 6, that would give me negative 15x. Negative 9 plus 7, that'd be minus 2y. And then negative 3z plus 3z, well, that's going to get rid of z. Now negative 90 minus 49, that's negative 139. So I have a second equation of negative 15x minus 2y equals negative 139. Let's go ahead and stack these two equations up side by side. So 31x plus 18y equals 193. And then we have negative 15x minus 2y equals negative 139. Well, I think it's obvious we want to just get rid of y. Because if you multiply the second equation by 9, you would end up with a positive 18y and a negative 18y, making it nice and easy to get rid of the y variable. So let's go ahead and do that here. I'll keep my 31x plus 18y equal to 193 the exact same. Now I'm going to take 9 times my second equation, and let's see what we get here. So you keep the 31x plus 18y equal to 193. Alright, this is where it gets fun. This 9 times negative 15x is negative 135x. 9 times negative 2y, well, that'd be negative 18y. Now, what is 9 times negative 139? That's not going to be a pretty number. Negative 1,251. But we can at least eliminate the y variable by adding these two equations together. If we do that, we add these two equations together, you would end up with negative 104x would equal, now we need to add 193 to negative 1,251. That would give me negative 1,058. Oh boy. So negative 104x equals negative 1,058. And they don't divide evenly. No. So you're going to get a really nasty number for x. That's going to equal 529 over 52. You get 529 over 52 for x. Yeah, not pretty. Not pretty at all. Now we can take our x value, stick this into any of these two equations here, and solve for y. Let's go ahead and do that. Good Lord. So I'll take 31 times the x value of 529 over 52 plus 18y, set that all equal to 193. Now we got to figure out what the heck is 31 times 529. Hold on a minute. Yeah, that's right. 31 times 529. You would end up with 16,399 over 52 plus 18y equals 193. Which now we can get the 18y by itself, that's going to equal, of course, negative 6,363 over 52. Good Lord. Which would give you a y value of negative 6,363 over 936. Which, good news is, does simplify. So 63 divided by 9, that's going to give you a y value of negative 707. 936 divided by 9 over 104. It's looking a little bit better, but still pretty horrific. Negative 707 over 104. Alright. Now that we know our x and our y values, take both of those, substitute it into any equation you'd like. And I'm probably just going to go with the top one so we can directly solve for z. Now, I am going to erase a little bit of this work here so we don't run out of room, because this is an insanely big problem. Sometimes you'll have that with these 3-variable equations. It can be absurd and ridiculous how long these can get and big they can get. So let's go ahead and take our x value of 529 over 52. So 3 times 529 over 52 plus 3 times our y value of negative 707 over 104 plus z, set all that equal to 30. Well, what is 529 times 3? 1,587. So we'd have 1,587 over 52. Now 3 times 707 is 2,121. So that'd be minus 2,121 over 104 plus z would equal 30. Well, we definitely want to get the same denominator, don't we? So we're going to have to multiply everything on the first term by 2. So 1587 times 2, that's going to end up being 3,174 over 104 minus 2,121 over 104 plus z. I would say we should actually go ahead and get 30 into terms of 104. So 30 times 104 would end up giving you 3,120 over 104. Yes, this is not pretty, is it? Alright, so we're going to go straight for z. So 3,174 minus 2,121 gives you 1,053 over 104. Now subtract that from this side. 3,120 minus 1,053 that gives you a z value of 2067 over 104. That was awful. That was pretty bad, wasn't it? Let me go ahead and erase some work over here too, so I can write the ordered pair at the very least. Or the ordered triple, I should say. So your x-coordinate is going to be the awful 529 over 52. Your y is going to be the awful negative 6,363 over 936. No, it's not. It's going to be negative 707 over 104. I was looking at the wrong line. I forgot I had simplified it. Negative 707 over 104. Then your z value will be the awful 2067 over 104. So you get the horrific order triple of 529 over 52, negative 707 over 104, and 2067 over 104. So you will sometimes get answers like that that are just god-awful. So that's really all there is to solving systems of equations with 3 variables, with 3 equations. So yeah, you're going to figure out an elimination method for 2 of your equations at once to get rid of one of the variables, and then do it again with another set of the 2 equations to eliminate the same variable. You'll take those 2 new equations of 2 variables, add them together, and eliminate them, and then you'll go down to 1 variable. And then you'll use back substitution to figure out the value of all the other variables. So that's it for this lesson. Next lesson, we are going to start the matrices unit, which matrices are a whole nother way of solving systems of equations. Next lesson, we'll just generally talk about what a matrice is, or matrix in the plural form matrices are, and even a little bit of matrice addition and subtraction and scalar multiplication with a matrix. So I hope everyone has a great day. Take care.